Who knows what it looks like, but it exists. The probabilistic method. We use the words likely or probable and the likelihood or probability every day in informal conversations. While making these concepts absolutely rigorous can be a difficult task, we will concentrate on special cases when a mathematical definition of probability is straightforward and conforms to common sense. The notion of probability. Let us assume that we toss a coin 4 times and we want to know the probability that we will get at least 3 heads. The number of all outcomes of the 4 coin tosses is 2 to the 4 equals to 16. Indeed, each coin toss can result in 2 possible outcomes. On the other hand, the number of favorable outcomes of our coin tossing sequence is 5. Indeed, the 5 favorable outcomes, that is, those containing at least 3 heads, are H, 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 T, H, H, T, H, H, T, H, H, and T, H, H, H. Our common sense now suggests that we defined the probability of getting at least 3 heads as the ratio of the number of favorable outcomes to the number of all outcomes. Doing that, we get that the probability of getting at least 3 heads is 5 over 16. This common sense approach is the basis of our formal definition of probability. It goes without saying that we will have to be a little more careful. For instance, the above argument assumed without mentioning it that our coin is fair, that is, a coin toss is equally likely to result in a head or tail. Definition 15.1. Let omega be a finite set of outcomes of some sequence of trials, so that all these outcomes are equally likely. Let A, which is a subset, equals to omega. Then omega is called a sample space, and A is called an event. The ratio P of A is equals to the absolute value of A divided by the absolute value of omega. It's called the probability of A. In particular, P is a function that is defined on the set of all subsets of omega, and 0 is less than equals to P of A, which is less than equals to 1, always holds. There are, of course, circumstances when this definition does not help, namely when omega and A are not finite sets. An example of that situation is to compute the probability that a randomly thrown ball hits a given tree, as the ball could be thrown in infinitely many directions and would hit the tree in an infinite number of cases. The above definition would be useless. We will not discuss that situation in this book. We will only study finite sample spaces. Note that if A and B are disjoint subsets of omega, then the size of A union B is equals to the size of A plus the size of B, and therefore the probability of A union B is equals to the probability of A plus the probability of B. In general, we know from the C formula that the absolute values of A union B is equals to the absolute values of A plus the absolute values of B minus the absolute value of A intersect B, implying that the probability of P of A union B is equals to P of A plus P of B minus P of A intersect B. A generalization of this observation is the following simple but extremely useful inequality. Proposition 15.2. Let A1, A2, A3 until AN be events from the same sample space, then the probability P of A1 union A2 union A3 and so on union AN is less than or equals to P of A1 plus P of A2 plus P of A3 and so on plus P of AN. Proof. We simply have to show that the absolute values of A1 union A2 union A3 and so on union AN is less than or equals to the absolute values of A1 plus the absolute values of A2 plus the absolute values of A3 and so on plus the absolute values of AN. This is true as the left-hand side counts each element of the sample space that is part of at least one of the AI exactly once, while the right-hand side counts each element of the sample space that is part of at least one of the AI at least once. The reader has already been subjected to some training in basic enumeration in chapters 3 to 7. Most exercises in those chapters can be formulated in the language of probability. For example, the question, how many 6-digit integers contain the digit 6, can be asked as, what is the probability that a randomly chosen 6-digit integer contains the digit 6? Therefore, we do not cover these basic questions again here. Instead, we close this section by 2 examples that show how counterintuitive probabilities can be. Example 15.3. In one of the lottery games available in Florida, 6 numbers are drawn from the set of numbers 1, 2, 3, and so on until 36. What is the probability that a randomly selected ticket will contain at least one winning number? Some people tend to answer 6 over 36 is equals to 1 over 6. To this question, they are wrong. That answer would be correct if only one number were drawn. Then the number of favorable outcomes would indeed be 6, and the number of all outcomes would indeed be 36. However, when 6 numbers are drawn, the situation is more complicated. Solution of example 15.3. Let A be the event that a ticket contains at least one winning number, and let B be the event that a ticket does not contain any winning number. Then clearly A and B are disjoint, and A union B is equals to omega, so P of A plus P of B is equals to 1. Therefore, it suffices to compute P of B for ticket not to contain any winning numbers. It has to contain 6 non-winning numbers. The number of ways that can happen is 30 choose 6. Therefore, P of A is equals to 1 minus P of B, which is equals to 1 minus 30 choose 6 divided by 36 choose 6, which is equals to 1 minus 0.3048, which is equals to 0.6952. So, with almost a 70% probability, a randomly chosen ticket will contain at least one winning number. No wonder you must have more than one winning number to actually win a prize. Note that when A and B are 2 disjoint events, then we say that A and B are mutually exclusive. In other words, it is not possible that A and B happen together. If, in addition, we also have A union B equals to omega, then we say that B is the complement of A. We denote this by writing A bar is equals to B. Example 15.4. 40 people are present at a party, and there is nobody among them who was born on February 29th. Adam proposes the following game to Bill. Each guest writes his or her birthday, just the day and the month, not the year, on a piece of paper. If there are 2 pieces of paper with the same date on them, then Adam wins. If not, then Bill wins. When Bill heard this proposal, he looked around and said, "Fine, there are only 40 people here, much less than the number of days in a year, so I am bound to win." What do we think about Bill's argument? Solution. The problem with Bill's argument is that he fails to note the difference between 100% probability and more than 50% probability. If we want to be 100% sure that there will be 2 people in the room having the same birthday, we would indeed need 366 people to be present. To have a more than 50% chance is an entirely different issue. In what follows, we prove that if there are at least 23 people at the party, then Adam, not Bill, has more chance of winning this game. In order to prove this, it is clearly sufficient to provide a proof for the case when there are exactly 23 people at the party, as any additional person just improves Adam's chances. Let us compute the probability that there are no two people at the party who have the same birthday. For that to happen, the first person's birthday can be any of the 365 possible days of the year. That of the second person could be any of the 364 days, and so on. So the number of favorable outcomes is 365 with braces under the index 23. Yeah, that's the special symbol used in this book. On the other hand, the number of all outcomes is obviously 365 to the 23. Therefore, the probability that there are no people in the room whose birthdays coincide is 365 times 364 and so on times 343 divided by 365 to the 23, which is equals to, if we cancel out the 325, that will be 364 times 363 and so on until times 343 divided by 365 to the 22, which is less than 1/2. Therefore, the probability that there are two people at the party who do have the same birthday is more than 1/2. Finally, we point out that the condition that nobody was born on February 29th was only included to make the situation simpler. Indeed, February 29th exists only in leap years, so the chance of being born on that day is 1/4 of the chance of being born on any other given day. That would make the outcomes in our sample space not equally likely, contradicting the definition of sample space. We could help this by changing our sample space from the 365 element set of dates in a year to the set of 4 times 365 plus 1, which is equals to 1,461 days of a 4-year cycle. That would make computations a little bit more cumbersome.